Okay, hi everyone. Thanks for coming to another Graphs and Matroids seminar. Today we have Natasha Morrison from the University of Victoria, who's going to be talking about uncommon systems of equations. Go ahead, Natasha.
Well, thank you very much for the invitation. It's lovely to be here virtually in Waterloo. Maybe one day I can in real life come and see. I guess so. Throughout my slides, I've got some nice pictures of BC because I think we're all missing travel. So this is my attempt to make people happy while I'm talking about math. So, okay, so yeah, I'm going to talk about uncommon systems of equations, which is, I guess, it's not really graphs and it's not really matroids. I am going to start by explaining the relation to graphs, and I am going to also explain a bit about kind of how you might think it's something to do with matroids, but perhaps there are slight differences later. Just Jim suggested this was a good idea so that people didn't spend time getting confused about whether this was something, a matroid question or not. I'm going to admit that I am not a matroid expert. So please, I know many of you here are matroid experts. So feel free to jump in as a point if if my matroid explanation is not good. Sorry in advance for that. So let's start by talking about graphs anyway. So maybe many of you have come across the very famous theorem of Goodman, which says that if you color the edges of the complete graph on n vertices in two colors, red and blue, then if n is very, very large, you're always going to have the density of monochromatic triangles being at least 1/4. So, right, so any way you color your edges, the number of red triangles plus the number of blue triangles divided by the total number of triangles, it's always going to be at least 1/4. You can't do better than that. One way of thinking about this theorem is you can say, well, what does this say? It tells us that a random two coloring minimizes the number of monochromatic triangles, because if you color the edges red and blue, each with probability 1/2, what's the expected number of monochromatic triangles? The expected density will be 1/4. So I guess it's kind of two ways of thinking about this kind of thing. So this is true for triangles. The next natural thing to wonder is to say, okay, what about other complete graphs? Is it still true that if you consider a KT, how do we minimize the number of monochromatic copies of, I don't know, a K4 or a K5? So Erdős made a very nice conjecture in 1962, which was that basically, right, so Goodman's theorem says that for a triangle, if you want to minimize the number of monochromatic copies, taking a random coloring will do that. Erdős conjectured that this is true for all t, at least 3 for kt. So again, the way you could think of this is saying Erdős conjectures that random is best for minimizing. Now, it's not to say that this is the only way you could minimize. So for example, if we went back to the triangle example, if you took a complete blue bipartite graph and you made the blobs in each side red, that's a very non-random construction. That's still got a really small number of triangles. But I guess one way of thinking about it is to say kind of random is best. So this is for the complete graph. You might also wonder, what about just a general graph? So Burr and Roster, I think, perhaps optimistically conjectured in 1980 that, in fact, this is true for any graph now. If you want to minimize the number of copies in a random two coloring, well, taking a random two coloring is going to do that for you. So we had Erdős's conjecture, which says this is true for KT. We have Burr and Roster, which conjectures that it's true for H. So this property of minimizing the number of monochromatic copies, so that I don't have to keep saying these words again and again and again, right? We can say that a graph H is common if the density of monochromatic copies is asymptotically minimized by a random coloring. So that makes my life easier because I don't have to say as many words from now on. So you can, so Erdős's conjecture says KT is common, and the Burr-Roster conjecture says every graph is common. Unfortunately, the conjectures are false. So in fact, they were disproved independently by Thomason and Sidorenko. So Andrew Thomason came, very nice paper, which shows that K4 is uncommon. So this disproves the conjecture of Erdős, which was for cliques, and also the Burr-Rotter conjecture simultaneously and independently. Sidorenko showed that a triangle with a pendant edge is uncommon, and this disproves the Burr-Rotter conjecture. But despite the fact that both these conjectures are false, since then, there's been a lot of interest in determining which graphs are common or are not common. So many graphs are known to be common in various families, for example, trees and cycles and even wheels, and perhaps more complicated things that are difficult for me to write in one slide. But there's, I think, one of the very interesting results about graphs that are known to be common is this result of Jaeger, Stoviček, and Thomason, which says that any graph containing a K4 is uncommon. So it kind of says, right, just having a K4 in your graph is enough to make this uncommon. You can do whatever you want elsewhere with your graph, but somehow just having this little K4 is going to kill any hope of it being common. So one of the results I'm going to tell you about in this talk can be thought of an analog of this theorem, but for systems of equations. So it would not be good of me to talk about common and uncommon graphs without also mentioning the property of being Sidorenko. So I'm sure many of you have heard of Sidorenko's conjecture. So the graph H is Sidorenko if the density of copies in a graph with fixed edge density is asymptotically minimized by a random graph of the same edge density. So I guess the way to think about this is common is kind of, it's a, right, you look at your graph, you've got red and you've got blue, and you want to count the red copies plus the blue copies. And that's always at least something. In Sidorenko, it's like looking at just one color, basically. So you can say the number of red triangles in this graph is at least the number of red triangles in a random graph with the same density as what you have here. I'm not going to spend that much time talking about Sidorenko, so I wouldn't worry so much about it. But I'm sure you've heard of Sidorenko's conjecture, which says that all bipartite graphs are Sidorenko. Perhaps if you haven't heard of it, you can convince yourself why it doesn't make sense to think about a non-bipartite graph for Sidorenko's conjecture. And in fact, the property of being Sidorenko, so without going too much into the definition, it took me a while to get my head around the Sidorenko definition, to be completely honest. So if you've not seen it before, I appreciate that you might not fully get it yet. But somehow, right, Sidorenko is a one color condition and common is a two color condition. And it's not difficult to see that if a graph is Sidorenko, then it's common. So in fact, a lot of the graphs that we know are common, they've actually, people have proved that they're Sidorenko. So the stronger thing is known. So trees, cycles, even wheels and such. Okay, so what about systems of equations? Or even single equations. So for example, x plus y minus z equal to 0. So let me just spend a little time setting up kind of the world that we're going to be thinking about. Also, please do sort of shout and complain at me if I'm not making sense at any point. There's no point me sort of going off talking to myself if you're confused. So what we're going to do for now, let's just think about single equations. So we've got, say, k variables, x1 up to xk, and our coefficients are going to be, you can pick them to be non-zero in your favorite finite medium group, or pick them to be, or think about them as being non-zero integers. So this is, I guess this is an equation. And you can define the solution set of the equation to be just the k tuples that satisfy this equation. So for example, if we consider this equation here over the integers, what are the solutions here? Well, they're parameterized. If we pick integers a and d, we can see that the solutions are parameterized by a plus d, and a plus 2d. this is just our, common three, I shouldn't say common, the usual 3-term arithmetic progression, right? And you can see that because of the way it's parameterized, you can see that this is a 3-term arithmetic progression. 2 examples are here. So what we're going to be thinking about is solutions in, right? So when we were talking about graphs, what did we do? Well, we said, okay, let's color the graph red and blue, and let's look at copies in the red and copies in the blue. So similarly here, what we'll do is we'll look at the world that our equation is living in. We're going to color, so for example, the integers, color them red and blue, and we can say, okay, what solutions are there in the red set and what solutions are there in the blue set? So for a particular set A, where A is a subset of whatever you want, you can define sol LA to be the solutions that are k-tuples just in this particular set. And so the kinds of questions that we've been thinking about are basically, what can you say about the number of solutions in a particular set? Or in terms of common, right? This is like saying, if we've colored the points red and blue, A is the points colored red, A complement is the points colored blue. What can you say about the combined number of the red solutions and the blue solutions? I don't know why the slide just appeared twice. So these problems have been thought about very classically. So for example, I'm sure you've heard of van der Waerden's theorem, which says that if you take n big enough and you color the integers 1 up to n in 2 colors, then you're always going to get a k-term arithmetic progression. So what is a k-term arithmetic progression? Well, it's just like a generalized, not generalized, but right before we had this 3-term arithmetic progression, a plus d, a plus 2d, and a k-term one is just a longer one. So here is like a little example of one coloring, so of 1 up to 9, but you can see, right, however you color this number 9, you're either going to get a blue progression or a red progression. And this is just some illustration, right? What does van der Waerden, it sort of says, well, when n is big enough, however you color your colors, you can't avoid having this k-term arithmetic progression. And in fact, right, this is true also where 2 is replaced by r and n depends on k and r. Very, very beautiful result, I think. So in terms of the kind of what we are, our notation, what does van der Waerden say? Well, it says the number of solutions for a KAP inside our red set plus the blue set is always at least 1. Right, so it's a question of the form, let's think about the solutions of a set of equations in a colored setting. So 3-term arithmetic progressions in particular are of interest to many, many people. So again, the famous Roth's theorem bounds the density of a set that has no non-trivial 3-term arithmetic progression. So Roth's theorem says if you want the number of solutions, so why do we say non-trivial? Well, obviously, if you have, say, AAA is a 3-term arithmetic progression with difference 0. So you have to say non-trivial. But Roth's theorem says that if you have a set with no solutions, then it's got to be small. And this is a very famous problem in additive combinatorics, and people all the time are trying to improve the best bounds on this set. I think there's some very, very interesting but difficult methods in this paper of Bloom and Sisask. Okay, so that's 3-term arithmetic progressions. People also prove similar things about 4-term arithmetic progressions, k-term arithmetic progressions. So this is, let's pay particular attention to this 4-term arithmetic progression because we're going to be talking about them a bit later. So this is a system of 2 equations, right? And each one individually is a 3-term arithmetic progression. So kind of the first equation says your first 3 variables are in a 3-term arithmetic progression. Your second equation says your second 3 variables are in a 3-term arithmetic progression. So together they're in a 4-term arithmetic progression. And Semeradi's theorem, basically it's like a version of Roth's theorem, but for k-term arithmetic progressions. But so all of this was pretty much kind of a background to where does this line of research come from? So people have considered questions about Sidorenko and common graphs. People have considered similar questions about systems of equations. So let's now think about the particular setting we're going to be in. So we're going to think about FQ, where Q is a prime power, and let's say Q is an odd prime power. This is just what I wrote before, and this is just a little bit of simplified notation. So here is what we are thinking about in our particular setting. So I realize that a lot of words just appeared on the slide, but essentially, right, the definition of common for systems of equations is it's exactly the analog of the graph thing that we talked about. So we're going to say it's common if the density of monochromatic solutions in any two coloring of FQ to the n is asymptotically at least the expected density in a random two coloring. So imagine n is very big. So our variables here are going to take, oh, sorry, did someone ask a question? Maybe not.
I think maybe someone was accidentally unmuting themselves, but I've muted them and hopefully it'll be okay.
So basically, right, we're going to take these vectors in where each in FQ to the n, we're going to color the whole family red and blue, and we're going to say, let's look at the solutions to this equation in the red color and the solutions to this equation in the blue color. And our system is common if the density of these solutions is at least what you get in a random coloring. Okay, so let me do a little another way of thinking about this definition. So here I wrote about the expected density in a random two coloring. You can actually write out exactly what this is in terms of sets for sensible systems of equations. So it basically just means that you don't have a couple of stupid things happening. I don't really want to go into the details there, but essentially for any kind of equation or system of equations that might be interesting, your definition basically becomes the number of red solutions plus the number of blue solutions is going to be at least 2 to the 1 minus k, where k is the number of variables in your equation or system of equations, the solutions in FQ to the n. I don't know why that disappeared. Sorry, I don't understand why part of the slide is appearing later than the rest, but yeah, this is another way of saying this is common. It's by looking at these sets. Okay, so there's a question of Sad and Wolf, which says, which equations or systems of equations are common or uncommon? So I guess, right, they were also interested in thinking about the Sidorenko property. So they basically said, okay, look, people have asked all these things for graphs, people have proved specific things for special systems of equations. What can we say in general about systems of equations? And so let me give you one small example of how you might think about this for single equations. Oh, there's a cat. Sorry, someone just had a cat on their camera. So let me give you, we're going to do an example for a single equation. What we're going to talk about in general is systems of equations, and that's the point I'm going to talk about matroids, because they're more related to systems of equations. So for a 3-term arithmetic progression, which is just this equation here that we talked about earlier, if A is some subset of FQ to the n, what we care about, right, is the number of solutions that are red plus the number of solutions that are blue. So we can parameterize the solutions in a different way. So we can pick x and we can pick y, and then in fact 2x, 2y minus x, this will give you a different parameterization. And this will help us, right? So this looks kind of yucky, but essentially what are we doing here? We're just writing the number of solutions in terms of indicator functions, and you'll see that actually it all works out really nicely once you bear in mind these indicator functions. So what is this? So we've seen that we can parameterize the solutions by fixing x and y. So the indicator function, it gives you a 1 if x is in the set, and it gives you a 0 if x is not in the set. So if you look here, right, this product here is going to give you a 1 whenever this particular solution is in the set A. And this is going to give you a 1 when this particular solution is in A complement. And right, we know that all the solutions have this form. So if we take the sum over all x, y, this is going to precisely count the number of solutions in A plus the number of solutions in A complement. But what we care about is the kind of density. So we just divide through by this, and this corresponds to dividing through by this on the other side. Now we can use the fact that the indicator function of A complement actually is just 1 minus the indicator function of A to rearrange this equation. I'm not going to do the calculation step by step, but you can hopefully believe me that if you substitute this in and multiply it out, what you end up with is exactly this, which is exactly this, which in fact, right, this is an equality here, but this is what we wanted to compare it to. So this is precisely the expected number of monochromatic solutions in a set of density size A, right? So this is like the red and this is the blue, and this tells you that 3-term arithmetic progressions are common. So this is very nice in the sense that actually for this single equation, for the 3-term arithmetic progressions, this argument gives you precisely what this is. So okay, it's very nice, but also perhaps it's not so interesting because you basically have a simple argument which tells you exactly what the density is, and you can see that this is 3-term arithmetic progressions are common. And in fact, so this is the argument, it generalizes to any equation with an odd number of variables. You can do exactly the same thing. Single equation. So yeah, they're common. And as I said, right, in general, this argument generalizes. So this is an argument of Cameron, Sidorenko, and Sarah, which basically says, in fact, not only are they common, we can say exactly what the number of solutions are here. So odd number of variables kind of for single equations, we understand. What about even number of variables? Well, Sad and Wolf proved that if you have a single equation, then your equation is common whenever the coefficients can be partitioned into pairs that sum to 0. So that's not a particularly difficult argument. You can do a kind of Cauchy-Schwarz type argument. They conjectured, in fact, that this was an if and only if. So whenever you have an even number of variables, it's common if and only if the coefficients can be partitioned into pairs summing to 0. And the conjecture was proved. So what I've done here, it was proved by Fox, Pham, and Zhao. What I've done is I've combined the stuff from the previous slide with the result of Fox, Pham, and Zhao. And this gives us a full characterization of single equations. So it tells us that whenever k is odd, right, that was the argument we saw an example of using indicator functions. We know the equation is common. And if it's even, then it's common if and only if the coefficients can be partitioned into pairs that sum to 0. So for example, an additive quadruple is common. Okay, so single equation systems are really, really well understood. What we're interested in is systems of more than one equation. So, right, so I guess the work of Sad and Wolf and Fox, Pham, and Zhao and Cameron, Sidorenko, and Sarah together characterizes one equations, but both Sad and Wolf and Fox, Pham, and Zhao have said, well, okay, we understand one equation. What can we say about more complicated systems? So what we're going to do is we're going to think about systems of equations. We're going to think about homogeneous systems of equations. So that just means that we've got some equations that are equal to 0. You can put something that's not 0 here. So again, for the single equation case, you can put something that's not equal to 0 here. It's not any more interesting than the case where this is just 0. It's the same arguments and techniques kind of go through to give you what you want to know. So for example, what we're going to be thinking about are systems of 2 or more equations. So for example, our favorite 2-equation system, the 4-term arithmetic regression, whose solutions can be parameterized in this way. So now I'm going to make a fool of myself by trying to say something about matroids. So does this have any relation to matroids? Well, so a simple binary matroid is a restriction of f2 to the r, but where you get rid of the 0. And the reason that, I guess, so you can think about matroids in other finite fields, but this is nice because they have a unique representation over f2 to the r. So you can, I guess it's easier to think about things when they have a unique representation. So my favorite matroid is the Fano plane, so what is this? Well, one way of thinking about it is you can say, okay, we have A, B, and C here that are linearly independent, and say a copy of the Fano plane in this space is I guess you've got all these points, A, B, and C, and they satisfy this set of equations. So we've got D being equal to B plus C, E is equal to A plus C, F is equal to A plus B, and G is equal to B plus E. And this is kind of demonstrated by this picture here. So the lines represent the dependencies. So on the one hand, right, the Fano plane it is, it's the solution of a system of equations. So you could say, right, let's color our points here red and blue, and we can ask questions. We can say, okay, if our system of equations is a way, right, you could say, okay, how is the Fano plane common? You could try and come up with an analog, right? If we color these red and blue, and this is the kind of thing we're looking for. So there are 2 differences kind of between what we're doing in our work and what you might want to do in a matroid analog. So firstly, when you're thinking about matroids, so it's important that A, B, and C are linearly independent here for this. This is the way the matroid is defined. When we're looking at solutions, we don't have such a restriction on A, B, and C. And I was thinking about this, and I was wondering, so somehow saying they're linearly independent is kind of like saying they don't solve certain equations, rather than, I'm not sure there's a way that you can express this condition in terms of I was thinking, is there some nice way to express this condition that gives more equations or something? But I think it's kind of the opposite, right? So what you're doing here is you're saying you've got these things that don't solve some equations, but also have these equations that so it's related in the sense that you've got these relationships between your vectors. You want to count the number of them, but it's kind of the way we're doing it. We definitely don't have a way of inputting this condition. And the other thing that's different, which I think is perhaps not so terrible if you wanted to try and do analogs of what we're doing, is that here, right, you're removing 0 from so you're not allowed A, B, and C, or any of these things. They're not allowed to be 0, which I think actually shouldn't make such a huge difference. It seems to be more of an issue, this condition on A, B, and C being linearly independent, in terms of if you wanted to use what we do, our methods, to kind of say something about matroids. I don't immediately see a way that you could somehow put this condition in. Although that's not to say that there isn't, it's just that I haven't sort of thought about it. But so hopefully it's kind of clear how what we're doing could be thought of as being related to asking similar questions about matroids, but there are these kind of 2 clear differences. That means it's not directly applicable. Does anybody who knows a lot more about matroids than me want to add anything to what I've said? If there's something that would be helpful for other people to know. I really, I've read a few things about matroids over the past few weeks, but I really haven't spent a huge amount of time thinking about them. So I don't want to confuse people, but I also think it's important to sort of explain how it is and isn't related.
Could I just ask a question about, so if if I don't want them to be linearly independent, that's similar to asking in graphs for things like homomorphisms as opposed to restrictions. Do the graph results all work for homomorphism?
I think, yeah, so definitely Sidorenko results, essentially you are talking about homo, it's the same. I think the difference between copies and homomorphisms ends up being lower order terms in most of the graph results. I think definitely, like Sidorenko is actually defined for graphs in terms of homomorphisms. And so my guess is that this is similar.
So it may not make a difference here. It may not make a difference if you don't ask for A, B, and C to be linearly independent, then it may not, like the counting may work in your favor and it just may end up being the same.
Yeah, it might be the case. Again, this is something I thought about a bit, but I didn't want to kind of go either way and say you definitely could or you couldn't. Somehow, like, I guess most vectors, right, and you've got a lot of things that are linearly independent, right? It could be, again, that the things that are not linearly independent actually are a small term compared to the ones that are. And so you're right. I was also thinking about this, but I didn't have a concrete enough thing to say to be able to say it does matter or it doesn't matter. You're right that it might be the case that you can do the counting and it doesn't matter. Although in terms of, yeah, I guess in terms of trying to, you'd have to sort of go through the proof, perhaps, where you didn't add this condition and then sort of later say that it doesn't matter. Somehow, I don't see how you could.
Yes. A good test case might just be to do A plus B plus C equals 0, and that will count triangles, except for the fact that if you're allowing 0, then you can have A, and 0 creeping in as solutions, and to see whether that makes a difference. So I think maybe the triangles case would be a good test bed.
Yeah, I guess it would be interesting in both cases, right? If either it sort of goes across nicely, or even if it doesn't, it would be interesting to say, look, something genuinely different is happening here for matroids. So yeah, I guess I didn't want to sort of, I haven't spent enough time thinking about it to be able to say for sure, yes, they're definitely very related questions. And I could believe that, I guess, right, some methods might work, but there might be things that do matter. Okay, so hopefully we're kind of convinced that perhaps we can say things for matroids, but perhaps there are things that we have to think more about to make sure that we're not cheating somehow. But okay, so that was I suppose a sort of sideways route to say, okay, we're thinking about systems of equations, which are very similar to thinking about. Oh, and the other thing is, okay, actually, very important thing is here in our binary matroids, we're in F2 to the R. Our results about uncommonness actually don't work for fields in characteristic 2. So okay, and then we're in matroid world where there are not unique representations. And okay, but again, there are relations. It's hard for me to be able to say what would work and what wouldn't right now. But it's definitely interesting. Okay, so just briefly, so what is known about 4APs? So I've just repeated the equation here. So Julia Wolf in 2010 proved that 4AP is uncommon over ZP. So, I mean, this is just another way of saying what that means. I mean, she found a construction that had too few monochromatic 4APs. And Julia Wolf's construction was based on a construction of Gauss, which comes from quadratic Fourier analysis. Now, both the constructions of Julia Wolf and Tim Gauss, they both really seem to use the geometric structure of the 4APs, right? You've got this kind of set which sort of jumps along evenly. And they kind of exploit that structure to be able to find these colorings that show that they're uncommon. So I guess people very much like Fourier P's, so they've spent lots of time thinking about them. So in particular, Sad and Wolf, I guess, used again a kind of generalization of what Tim Gowers did to show that Fourier P's are uncommon over F5. And so all of this work together on Fourier P's led them to believe that it could be likely that any system containing a Fourier P is uncommon. And I guess the hope was somehow, right, that the Fourier P plays the role of the kind, like the K4. So remember I said any graph containing a K4 is uncommon. So somehow just having that K4 is enough to ruin any hope of saving yourself by adding other things. And the Fourier P, right, has this special structure that somehow suggests that you can't do something to then make it common. So I guess we spent some time thinking about this question. Let me just clarify what I mean for you for a system to contain a Fourier P. So, right, so we've got a Fourier P, it looks like this. So you can say, okay, it contains a Fourier P. One way of thinking about it is we add some other equations to it. So we've got these two Fourier P equations and we add some other equations, and that's a system containing a Fourier P. But just an observation which you've probably made that I'm just going to point out is that a Fourier P, you can express it in many, many different ways. So if we, somehow the best way to think about this thing is to think about the parameterization of the solutions, because if you add multiples of these equations to each other, I mean, it's still a Fourier P. It just doesn't look like one anymore necessarily, right? So the best way of thinking about containing a Fourier P is to kind of say, okay, you've got a system which when you parameterize the solutions, there are these 4 coordinates. Oh, sorry, I clicked. There are these 4 coordinates that are that can be parameterized in this special way: a plus d, a plus 2d, a plus 3d. So you've got just these 2 integers, a and d, that are determining these 4 coordinates. And then the star just means you've got anything else here. And it's also, right, as we saw with the 3AP, the solutions can be parameterized in lots of different ways, right? We saw that for the 3AP, we saw 2 different ways. So just, yeah, this is just one way of thinking about the 4AP. Okay, so what does our theorem say? Well, it says, actually, their question or their conjecture, it's true. So it is the case that if your system contains a 4AP, then it is uncommon. So, sorry, that should say odd prime power. But so we've got FQ, and Q is some odd, oh no, sorry, when Q is at least 3, yeah, okay, it needs to be an odd prime power. Sorry, I'm just being silly. So I've said let L be a sensible system over FQ. That sensible in the sense that I mentioned earlier, there are sort of silly things you can do. Like if you add an equation, x1 equal x something new, well, these sort of trivial dependencies, if you add a new variable and make it equal to your previous variable, it's not particularly interesting. But yeah, so sensible just is let's remove silly things that you probably wouldn't want to think about anyway. So yeah, if L contains a 4AP, then it's uncommon. So for example, a 5AP is uncommon because these are the coefficients. I guess, right, this is a way of writing the 5AP. We've got these 2 equations of the 4AP, and we've got this x1 up to x5 to 5AP. So that's very nice, I think. So we've got this analog of any graph containing a K4 being uncommon. We can say any system containing a 4AP is uncommon, but in fact we can say more. So one way of imagining your 4AP is thinking that if it's a system like this. So very much abusing notation here. Let's just call a system containing a 4AP being a system that sort of contains a solution where part of it is parameterized like this. So right, I said you can pick 4 of your coordinates, and the solution space is parameterized in this way. So we can say, okay, if L contains a system like this, then it's uncommon. But in fact, the proof goes through to show that if L contains any system where you've got 4 coordinates parameterized in this way, then it's uncommon. So somehow this is actually incredibly general. This is almost, so we've got these 4 variables. So imagine just making 2 equations on 4 variables, and you're picking your coefficients. Essentially, almost like this is practically all pairs of equations on 4 variables. So this is just, these are, you want A and B and C and D to be non-zero, and you want this AD minus BC to be not equal to 0. But this says, right, you've got this huge family of systems. So somehow we like to think of this as saying that actually this geometric structure of the 4AP, the fact that you had this very regular intervals in your parameterization, somehow that's not important anymore. It's something else that's being used. Well, I mean, what's being used is that it can be parameterized in kind of this way. I guess this is all we need really for that to be true. So yeah, the coefficients, right, the special kind of geometric structure of the 4AP doesn't matter because we don't really use that in our proof. Okay, so how much time, when do you want me to stop talking?
I think anytime like between 50 and 55, so like 5–10 minutes.
So maybe I'll briefly give you an idea about the proof and then we can talk about open problems. Okay, so a different way of, I'm just going to tell you about the very kind of key part of the proof. So another way that you can think about, so we had this definition of common, and we said, okay, you can write the definition in terms of the expected density of a random set. You can write this definition in terms of saying the number of solutions in this set plus the number of solutions in this set is at least something. You can also write the definition equivalently using functions. So there's a standard kind of way to go between functions and sets. So think via indicator functions, right? So morally speaking, right, we saw that we can kind of count the number of things using indicator functions. There's a way that you can write the definition of commonness using actual f functions. So here is this equivalent definition. And again, this sensible just, the reason this is there is because if it's not sensible, this k is not k anymore. But so the kind of functional setting basically says that, so this is the average weight of solutions under f. So right, for each solution, you take f of this, each coordinate. So f is just some function from fq to the n. You take the product of the kind of the weight of your solutions. And so the equivalent definition says it's common if and only if for every function like this, then this is like the weight of the solutions in a half plus f plus the weight of solutions in a half minus f is at least something. You can believe me that this is an equivalent definition. This is why does it help to think about functions? Well, then you can use Fourier analysis to do things with your functions. There's a lot of, I used to be very scared of Fourier analysis, but there's a lot of really nice kind of things that are not too complicated. That especially if you read the kind of one equation papers, there's these really nice ideas where something just comes out really clean. It's like, oh, you just, take the Fourier transform and, oh, this is equal to this, and you just have to, it's very, very nice. So that's why we like functions. So our main theorem, kind of our main technical theorem from which our other theorem follows, says that it says, okay, we've got a sensible system is uncommon if there exists some function, the average of the function is 0, such that when you take, so remember that this is just the average density of, or the average weight of solutions under the function. But essentially, right, I haven't written a lot of details here, but what it's saying is, okay, we can show that a system is uncommon if we can find a function f such that when you take the sum over these critical systems L, which are subsystems, if we can find a function that works so that the sum of these things is less than 0, then we can show that the system is uncommon. Now, why does this help? Why is this not making this even more complicated? Well, these critical subsystems always have rank 1 or 2. So as we saw before, systems of 1 equation are really well understood, right? And systems of 2 equations, there are things you can do, but hopefully you can believe me that somehow trying to construct a function for a system of 2 equations is much easier than trying to construct a function for a system of 100 equations. So somehow it's saying, okay, we can show our system is uncommon if we can simultaneously find some function that works for just for the rank 1 and 2 special subsystems. So that's why this is what we use to prove our theorem. And I guess so the key point is that it reduces the problem to showing something for these low rank subsystems. And how do we find this function? Well, we kind of use ideas that come from this construction of Gowers using quadratic Fourier analysis. So essentially, I'm just wondering how much to say about this or not. I realize at some point, if I don't say enough, it just makes no sense at all. But I guess the point is somehow it's very, very easy for rank to make it's very easy to find an F so that the rank 1 systems have a very, very small weight here. Because you can do that, you just have to make the non-trivial Fourier coefficient small, and there's an idea of Gowers which allows you to do that very easily. So that the hard thing, I mean, these become a lower order term. So then what we care about are the rank 2 systems. This is just technicalities. What we care about is the rank 2 systems, and in fact, what we can do is we can create a kind of operator that works on our function in a way that basically pulls out this 4AP system, very roughly speaking. So somehow we can find a function that when you put it all on all of these systems, what the dominant term, it's going to make things small unless it's a 4AP. So then all we have to do is do something for the 4AP. So let me say very, very hand-wavily speaking, we define a function that basically says everything here we don't care about unless our critical system is the 4AP. And then we have to do something to win on the 4AP. So that's kind of nice. And then the same other thing, obviously, when we're playing the more general theorem, 4AP here is replaced by whatever our 4 system is. Okay. Yeah. So this is, again, just the key point. We reduce the problem to showing something for low rank subsystems, and we can use things from Fourier analysis that are not as scary as they originally appear when you read these papers. Okay, so let me just maybe give some concluding remarks. So one thing that I think people always ask when I tell them what we're doing about systems of equations is they ask, is there some relationship between equations and graphs? So is it the case, right, that certain systems of equations correspond to certain subgraphs? Can you translate your results between the two? In the Sadwolf paper, they have, I guess, a kind of nice discussion about some particular sets of equations that correspond to some particular graphs. But I don't think that there's no kind of general correspondence between these things. It might be the case that there are a few very special things that could happen. But what is interesting is that I think a lot of techniques that come from the graph setting can be used in the equation setting and vice versa. So somehow they're very related because similar techniques work for both sets of problems, but I don't think it's the case that somehow, at least it's not obvious to me how proving something for systems of equations would obviously then imply something for graphs, other than perhaps you could try and use the same technique. So I've talked a bit about systems that are uncommon. So how about briefly, what about systems that are common? So this is the theorem that I talked about for one equation. that was the combination of these three authors. So for single systems of equations, this is very well understood. Sorry, not systems, single equations, this is very well understood. So in particular, right, if k is even, it's common if and only if the coefficients can be partitioned into pairs that sum to 0. So this generalizes to systems of equations. So if we take kind of any system of equations where the pairs match up in a way that sum to 0, like this, for example, then this is a common system of equations. It's perhaps not so interesting. You can stick things together. There's in kind of, so I don't know how familiar you are with results about Sidorenko graphs, but there are various results which sort of say that tree-like graphs, where you're sort of sticking them together in certain ways, in tree-like ways, they're all Sidorenko. You can do analogous things with systems of equations too. So you can kind of stick them together and make kind of tree-like systems of equations. So we have a very large family of systems that are common, but they all have this very, very structured kind of setting. And we don't actually know of any systems that are common that don't have this really strong kind of, like basically, right, they decompose in a very rigid way into individual Sidorenko equations. So these ones where these pairs match up. So we have a large family of common systems. In fact, our proof shows that they're Sidorenko. And that's actually a paper which hopefully we're going to put on arXiv this week. And as for graphs, Sidorenko implies common. We also have a large family that's not Sidorenko or not common, right? This is this theorem that includes any system that looks like this, for example, the Fourier P. So we've got lots of things that are uncommon. We've got lots of things that are common, but we're still pretty far from completely understanding systems of equations. So for a single equation, there's a really clean, nice classification. For systems of equations, it seems like it's much more complicated. And we have particular examples where kind of they are common or they're not common, but for weird reasons. So in particular, for the single equation case, what seems to be important is the additive relationship between your coefficients. For a system of equations, we have some ones where we can show they're kind of common, but it depends on the multiplicative relationship between your coefficients. And I realize that's quite a vague thing to say, but I mean, it suggests something really different is going on that we don't actually understand very well yet. So here is just, if you wanted to start thinking about this, here is quite a small kind of simple question to understand that I think is interesting. So at the moment, every system that we know that is common, the individual equations have coefficients that sum to 0. And we call that translation invariant. Does there exist a system of more than 2 equations, two or more, that is common but doesn't have this property, where the individual equations have coefficients that sum to 0? So for one equation, this condition is necessary, right? Because you have to have the things pair up. For 2 equations, we don't know. And this is something I think it's a very simple question. It's interesting. I think that's the end. But thank you very much for listening.
Awesome. Thank you so much, Natasha. Let's everyone please unmute, and then I'll count to 3, and then we'll clap. 1, 2, 3. Awesome. Does anyone have any questions?
I was wondering if, there's a theorem about K4. Are there other graphs with the same property that if you have those, you're uncommon?
Not off the top of my head. Although that's not
wheels.
I think I'd have to look it up, but Sorry, I feel like that's something I should know, but I don't remember.
Okay, thank you.
Does anyone else have maybe one more question? I was going to ask actually directly about like the converting graphs to the systems of equations, but you already mentioned that. So
yeah, I think the Sad Wolf paper gives a couple of examples of things where you can see how systems correspond to graphs, but I think they, at least in my opinion, they don't correspond in the way that's going to be enough to be able to translate results. So you can, certain kind of Cayley graphs, you can see as systems of equations, but somehow that's not good enough to be able to say something about common, because you're not, right, you're inside Kn, you're not inside a Cayley graph. But yeah, okay, I do. I'd be very interested if anyone could come up with some really direct way to translate results. I don't know how to do it.
Interesting. All right, well, thanks again, Natasha. I'll end the recording there.